So let's look at the following example. Let's show that the function f of x, 4x to the fifth plus x cubed plus 7x minus 2, has exactly one real root. So the first thing we need to go over is exactly what does it mean to have a root. A root is a number c, such that when you plug it into your function, you get 0. And something we're going to need to use here is the intermediate value theorem. Which we discussed previously, I believe, but if not, I'll mention it here. It says if f is continuous on the interval a to b, and if f of a is not equal to f of b, and k is any number between f of a and f of b, there is at least one number c in your interval a to b such that f of c equals k. So I need two numbers where I plug them into my function, they're not equal, and I'd like, because I'm looking for a root here, I'm looking for a root, I would like to have a number smaller than 0 and a number bigger than 0. So if I plug in, let's write down our function here. If I plug in 0 into my function, I get -2. And then if I plug in 1 into my function, you're going to get 4 plus 1 plus 7 minus 2, you're going to get 10. So here, f of 0 is not equal to f of 1. So it looks like I can use the intermediate value theorem. The one thing we need to make sure is that our function is continuous on this interval. Well, again, I have a polynomial. That means f is continuous everywhere because it is a polynomial. So the intermediate value theorem, I'll just abbreviate IVT, tells us that there exists a number c so that c is between 0 and 1 and f of c equals 0. So in the intermediate value theorem, I'm using the value k is 0. This tells me that my function f of x has a real root. C would be that root because when I plug in c into my function, I get 0. So that tells me I have a real root. So we've shown that it has a root, but now we need to show it has exactly one. So the way we do that is we're going to suppose that it had two. Had more than one, so suppose f of x has at least two real roots. So I'm going to call the two roots a and b. So there exists an A and a B that are not equal, but when I plug them into my function, since they're both roots, they output 0. So now I can use Rolle's theorem. By Rolle's theorem, there exists another number D such that f prime of D is 0. Now technically in Rolle's theorem they use the letter C here, but I've already used the letter C, so I went with D. But let's think about this. We know what our derivative of our function is because I have a specific function. I can calculate the derivative. Well, if I look, this is x to the 4th. The smallest that can be is 0. So that whole thing, the smallest that can be is 0. And the same thing over here. The smallest this could be is 0. So this whole thing right here, these are squares with positive coefficients. The smallest that could be is 0. So this derivative has to be at least 7. But there's our problem right there, is that we said, so f prime of D equals to 0 is impossible. So this tells us that we made a faulty assumption. In particular, there aren't 2 real roots. There aren't at least 2, so I can now say f of x has exactly 1 real root.